Good to be here. Thanks for coming. This is me. I'm the original author of Apache Calcite, although there's a lot of developers these days. Very active in open source, and I'm an architect at Looker. So the talk today is kind of going to be kind of a meandering selection of topics. What I'm trying to do is, my background is in building relational databases, in particular query optimization, but other things as well. And I'm drawing the parallels between the kind of data engineering you need to do to build the whole system, a system which includes data sources from perhaps third-party services, all the way through the data center and an interactive analytics system, comparing that to what's going on inside in the internals of the relational database. And looking at how we can apply some of those techniques, some of the learnings, to make the pipeline run more efficiently and make the users happier. So first of all, just let's look at what a database does and what a database is. So I guess the first question everyone asks is, in order to define what a relational database is, or what a database management system is, you should look at the alternative, which is just a file system with a program on top of it. How is that different? The answer is it's not really very different. The database is storing its data in files under the covers. In the case of a file system, you write a program in Python or C or whatever your favorite language is. The database also has a program that's running, and that program is a query. The difference is that the program that you run against the database is in a higher level language. And that gets translated into an internal program, an execution plan, which is what the database actually uses to access the data. So you've introduced this level of indirection between the actual, the question that the user asks and what the database actually executes. And that level of indirection is super important. The files are probably in fairly similar formats in both systems. So let's suppose we want to we want to do a program which does a join between two files which are largish, right, 100 million records in each. It's impossible to write a program that does an efficient join between those two files, or rather it's difficult, but it's easier if we just say, well, let's just sort the two files on their common key. Then we can write a very efficient program because it just does a merge. If you are the programmer that was responsible for that task, that's a significant effort because you need to rebuild these files and you need to rewrite your program. If you're using a database management system, that's extremely easy because you just write a join query, and perhaps the first time you run it, the data isn't sorted and the join query takes a while. And then you say, well, let's create an index on this, and the query runs really fast. So because the database has been regenerates that program every time you ask a query, and furthermore, it regenerates it based on the data structures that are available, you get this performance improvement. So the database system is literally managing the data. And furthermore, the database doesn't, when you create an index, of course you're not resorting. You're not taking the same file and sorting it. You're creating another file, which is a redundant copy of the data in a different sort order. Because it may turn out that the file in its original sort order or in its original organization is still, really useful for other kinds of queries. So that's another kind of recurring feature in database management systems is redundant copies of data. So there's various kinds of value that the DBMS adds. I mentioned abstraction, this fact that there's a high-level language which translates to a low-level language. You have to have that declarative language. You can't translate, for example, it's difficult to translate a Python program into something lower level because it's difficult to understand and rewrite something which is a Turing powerful language. SQL is sufficiently unpowerful that we're able to fully understand it and optimize it. You need a query planner to do that transformation, taking into account the algorithms that are available and statistics. The database makes it easy to reorganize the data, which is changing sort orders. We'll talk some more about that later. And then a bunch of other stuff like governance, metadata. And I'm going to propose adaptability, which is the ability of the system to respond to changes in workload. So respond if people are querying some data they've never queried before, or they're querying it in ways that haven't been queried before, the database will basically self-tune because of the way it's built, so that it starts running faster. So now let's look at what I claim is an analogous problem of the data pipeline. So here's a simplified diagram of a data pipeline. You're reading from sources. Perhaps these are cloud services that you use to run your business, and you want to load it into a cloud database like BigQuery or something. Since this is the modern ETL process, you tend to do the load first, copy the data into your cloud database, and then you do various transformations, basically refining the data into data sets that you can then use for whatever's downstream. So since this is a cloud database, it receives SQL queries. But if we add users to the picture, they probably don't want to speak SQL. They may be able to speak SQL, they may be comfortable, they may be somewhat comfortable, but it may not be the most efficient tool for the job. So probably for interactive business users, they probably want some other language, some higher level language. So you can kind of see the same pattern emerging here of having a low-level language, and we need a higher-level language to make things easier for users and to make things easier to manage. So if we go back to this old diagram of the file system versus the DBMS, I'd argue there's the same kind of progression from the DBMS to the analytic system, where the DBMS is in the heart of the analytic system, but we've got a higher-level declarative language on top of it. And the difference is the intended users for this. Analysts, are happy writing SQL statements. Business users may or may not be able to, but they're more comfortable in working in a higher level language. Whereas programmers want to, write programs that access the individual bytes of the file. So let's look at some of the tricks that databases use, and we'll see the kind of parallels to how those tricks could be used in the overall system. So one of the main tricks is reorganizing data. Often it means creating a redundant copy of the data. So one of which is taking the file and sorting it in a particular order. And then when you've sorted it, so I don't know whether the text is easy to read. So we've sorted it on A, B, C, C. The keys are now in sorted order. We can add an index, which basically tells us where's the first record that starts with A, where's the first record that starts with C. We can partition the data. In other words, put odd-numbered records over here, even-numbered records over here. We can replicate the data, so we can have one copy of the data in Tokyo, another copy of the data in New York, that kind of thing. Or perhaps just have one copy of if we've got a small table that everyone's joining to, we have one copy of that data in every node in the system, so we can join to it. And then lastly, summarization, which is creating a table which is grouped by, which is rolled up on quarter or month or department or whatever. These are all tricks that are creating redundant copies of the data. Often it's the whole data set, or perhaps it's created by some query on the data set. And then lastly, caching, which I would claim, caching is basically a process of copying data from disk into memory. You don't change its logical content, but you obviously change its physical format. You change it into a format which is suitable for memory. And I claim that caching is really just, it should belong on the previous page. Because caching, all you're doing is reorganizing data. You're converting it into a different physical format, so it has different characteristics. It's in storage, which is much more expensive, but has a lower latency. So I claim that the database makes the decision to bring some data into memory, and it makes the decision to not flush it out of memory. It's basically doing data optimization in the same way as those previous ones. Briefly, I'll introduce Apache Calcite, which is a project I founded about 6 or 7 years ago. It is a framework for building, well, you can think of it as a kind of a template for a database management system. It includes a SQL parser, but the heart of it is an implementation of relational algebra and a query optimization framework. It's used by a lot of projects and products, people, in the same way that no one writes a parser from scratch these days. If you're writing a database, it makes sense to start off with a relational algebra system. You tell it about your operators, you tell it about the the transformation rules you want to apply to those operators, and Calcite will basically help with the process. You can add your own statistics, for example, to drive it along. It's an Apache project, which means we work according to the Apache community model, which means there are, among those organizations that are using this and contributing to it, there's a lot of companies which are competing with each other, but Apache provides this level playing field so that these people can work collaboratively and not conflict. So relational algebra is the kind of mathematical underpinnings behind SQL and most other query languages. It's based on set theory, and it's a set of operations that you can do on sets, such as filtering a set, applying a function, and only leaving values in the set which fulfill a condition. So a SQL where clause is basically a filter. Aggregate operation is like group by. So this is the kind of the raw building blocks that Calcite and the query optimization rules are dealing with. The way Calcite's optimizer works, which is the industry standard way of doing this, is by algebraic rewrite. So we have algebraic transformation rules that recognize particular patterns in the algebra and then rewrite it to something which has the same semantics. In other words, it always produces the same results as the original query. But it may, we hope, be more efficient. So in this particular case, just flicking between these two slides, we've taken a filter and we've pushed it down into one side of a join, which means there are fewer records going into the join, therefore the join is probably faster. But combine this with maybe 100 other rewrite rules and you can start to do some pretty significant improvements to a query plan. One of the other things that Calcite and SQL provides is views. So when you define a view in SQL, what you're basically doing is defining a relational algebra expression. So when you define this view called managers, when I use managers in a query, managers looks like a table, but actually what I'm saying is when I include what looks like a scan of the table managers in a query, what I actually mean is I want you to substitute this blob of relational algebra in its place. So it's basically telling the system to do tree substitution. And this is a useful thing because it allows you to kind of hide the complexity of your application. You don't have to include that query every time you want to do a query on managers. It doesn't cause any data to be stored, so it's something that happens, all of the magic happens at prepare time in the query, but it makes your application simpler. So after expansion, we've now got a project that's reading from a join. Okay, materialized view is another important concept, and unfortunately, it has a very similar name to view, but it's almost the exact opposite. So when you create a materialized view, it does store data on disk. So when I create this materialized view emp summary, I'm saying, in addition to the employees table, I want you to create this other table with employees grouped by department number and gender. And just leave it there because I might want to use it in some future queries. And unlike create table as select, which is fairly similar, the system actually remembers where this data came from and it maintains that relationship. If I update the employees table, the system will also update the materialized view. So that when a query comes in, this query doesn't reference it references the employees table. It doesn't reference the emp summary table. In fact, the person who wrote that query may not know that emp summary existed, but the system is smart enough to realize that this is something that can be answered using the emp summary table, and the emp summary table is smaller, therefore it is able to rewrite it. And in order to rewrite it, it's actually quite a complex process that the optimizer has to recognize in the query this common sub-expression, which is the same as the defining expression for the materialized view. And because those are identical, it can then substitute the emp summary table into that part of the query. We've still got a filter on top of it. And in some cases, you actually have to rewrite the query a little bit to make what the lower parts of the query identical to the materialized view. Nevertheless, it's an incredibly powerful thing. Actually, a database index is, in a sense, a materialized view. It's a copy of the data where you've just applied a sort operation and projected perhaps a smaller number of columns to it. So materialized views are one of these, when I was talking about these different ways of organizing data, materialized view is this concept, even if a database doesn't call it that, it's this concept that allows the database to say, hey, you've asked me to query this data, but I'm going to query this data over here because I happen to know it can answer your question and it can do it faster. Okay. Analytics. So I work for Looker, so my job is figuring out how to make Looker faster and easier to manage and make the users happy and make the data engineers that are populating that, allowing the whole organization to be productive. So my examples will be drawn from Looker because that's what's in my mind. But all of this would apply to virtually any analytics system. So in Looker, Looker's based on at the heart of Looker is a language called LookML. It's basically a programming language. It looks somewhat like JSON. This is how you define your business views, how you define your data models. So here we're defining a view. It's not a SQL view. It's a business view called orders. And it's based on implicitly, it's based on a table called orders. So we can define a bunch of dimensions and measures and expressions and so forth. And this is the kind of high-level abstraction. There's another thing called an explore. This is the high level of abstraction on top of your relational database. And by the way, paradoxically, people like writing code. Code is just easier to manage than diagrams. People like the fact that you can diff it and merge and store it in Git and all that kind of stuff. And using this, you can build dashboards on top of these views. And then you can browse. This is an explore, which is basically a view of the raw data, but perhaps you can apply some visualizations as well. And lastly, people tend to edit this in a web-based IDE that gives you access to the code, but also gives you access to the model and so forth. So in that context, where we've got materialized, we've got business queries, and we've got a model which consists of business views. What are these data flows which are going on between these tables? Because that's the data engineering pipeline. And I claim that, the question is, who is actually responsible for making sure these data flows happen? Who's responsible for making sure this table gets populated, this job gets run? And the default answer to the question is the data engineers own it. But that's not a very satisfying question for anybody because there are users who need a particular table to be populated in order to run a report. And the data engineers are just too busy to be able to respond to that request. And furthermore, no one anticipates that someone is going to start querying this 10-year-old data set, and therefore there aren't indexes created for it. So the smooth flow of this data is a problem that needs to be solved in order to make everyone happy. And furthermore, the data engineering is not a static problem. It evolves over time. People add new reports. you've got a data scientist that wants to extract a file from this system. Perhaps we want to cache some data in memory. So how do we approach this? The default answer is this is all the responsibility of the data engineer. I would claim that we want to kind of hand power back to the users and let analysts control certain aspects of this pipeline to be able to create what they need. The system should be able to self-tune and create data sets as it needs them. And sure, the data scientist can write programs in Python or whatever to get the data that they need. If we reduce friction, everyone gets what they need. They get to go home on time. And the data engineers aren't just, frustrated because they seem to be the cause of everyone's problems. So here's another LookML view. But what we've got inside this is this construct called the derived table. So this is the means by which the analysts can get what they want. And we call it ETL Lite. And I think it's a strength of Looker, but I claim that it's something that should exist in any analytics product or any analytics architecture. Is this what we've declared is this derived table. So we've declared this view on this table called customer order facts, and it doesn't actually exist yet. So when someone uses this view in a Looker Explorer or dashboard or whatever, the system will go and create this table, which is called a derived table, based on that SQL statement. So it basically does a little mini ETL job. And it's probably quick and dirty, and it's probably, it probably doesn't conform to the enterprise's policy about, when you should be creating temporary tables and so forth. But it gets the job done, and at least it's on there in record in the model file, and it can be upgraded to a real ETL job in due course. Here's another kind of derived table. It basically is doing the same thing, but its source is not a SQL statement. Its source is an explore. In other words, something I've defined somewhere else in my Looker model. I'm defining a table that contains the result of reading from that business view. So this allows me to add richness. It also allows me to add efficiency because I'm computing this thing once, and it will basically use this derived table until the data goes stale. So there's various flavors of derived table. I've been talking about persistent derived tables here. There's also something called an ephemeral, and a persistent derived table is kind of like a create table as select. When you first load up the dashboard, it literally does a create table as select. An ephemeral derived table is kind of like a view. It's just expression expansion, and the expression will be substituted into whatever query gets run in the system, but it doesn't create anything on disk. So whether you use an ephemeral derived table or a persistent derived table, it depends on kind of amortization. How many, is it worth the effort of creating this, running this expression once and using it multiple times? Or if you're only going to run it once, probably you don't need to store it anywhere. And then lastly, transparent derived tables, which I would claim, are analogous to materialized views. So the basic persistent derived tables and transparent derived tables are, this is a feature under development, by the way. It's not currently in the product, but it's top of my mind, and it's where we're heading. It still creates the same amount of data on disk, except that it remembers where it came from. And you can use it in a query that doesn't reference that particular table by name, which means that you get this kind of magical speed up across the system for anything that is accessing that data. You don't have to rebuild your existing business models, your existing reports. You get this magical speed up. So making this process of tuning is a a complex process, and I'm not really going to address all of these points, but just to describe all of the things that need to happen in order for this to work. Somebody or something, some system has to figure out which materializations or which derived tables to create. As I described it there, it is a user, the person that writes the LookML model. Or in the case of a DBMS, it's the DBA who writes the create materialized view statement. Somebody has to populate them with data. In the case of Looker, it's created, when the data goes stale, it's recreated the next time it's used. We need to maintain it. It may be possible to maintain these things incrementally. Depending on how complex the expression is, we may not be able to maintain them incrementally. We may have to do a full reload. Somebody, and that's generally Calcite, has to see an incoming query and realize that it can be rewritten onto to use the materialized view. And that's a pretty complex piece of logic that's required to do that. We're forever making that logic smarter, and the fact that there's a lot of different companies and organizations contributing to Calcite means that we're kind of sharing our intellect. That is forever getting better, but as they say, being a query optimizer person is a job for life. The problem is just never done. We need the system to adapt, which is not just, I've looked at the queries over the last month and I think we need this new materialization. If someone's is running an analytics session right now and they're analyzing this data, we want the system to adapt to that pattern of behavior now, and not wait until tomorrow. So caching is a simple and easy and straightforward and pretty effective form of adaptation where you read this data, it leaves the data in memory, and therefore the next time I read it, it comes back faster. But caching, has limited power if the data you're reading is, a terabyte in size, and you don't have a terabyte of memory. And we need a rich algebra. Relational algebra is pretty rich, but if you're dealing with things like, nested collections and windowed aggregate functions and user-defined functions, it can be difficult for the system to keep up and to be able to make all of the necessary rewrites it needs to. Here's kind of a sketch of how Calcite offers some support for designing these summary tables. So this is answering the question of who designs the summary tables, the materializations. So Calcite has a structure called a lattice, where you basically tell it about a star schema. You say this, in this case, customers table is joined to the sales table is joined to the customers and the product table, and the product is joined to the product class table. And you say, once you define that, you're basically saying to Calcite, watch out for incoming queries that access one or more of these tables. And watch the query frequency of, watch for which roll-ups are occurring more often. Are people often, aggregating on the level of quarter or, zip code or whatever? And what will happen is it will start recommending particular summary tables at a particular level of aggregation based on that lattice. Now, I use the word lattice because it's a mathematical concept of a graph which has a top node and a bottom node. So let me just explain what the terminology means. So we've got these, simple example, we've got 5 columns, zip code, state, gender, year, and month. And the raw data is, for the sake of this example, 1 million rows. And if we just say count star, we get 1 row back, which is grouped by nothing. If I group by state, I'm going to get 50 rows back. If I group by state and year, I'm going to get 5 times 50. I'm going to get 250 rows back. So this is a higher level of aggregation. This is more granular. Every single item in this graph is a possible group by clause and therefore a possible summary table. We don't want to build all of them. There is a property that if you, for example, have a summary table on, let's say, year and month, we can roll that up to year. So that's what the line between y comma m and y is basically saying we can make that roll up. And the numbers here are kind of estimates of the number of rows that are going to be in these things. Zip code and state, there's fewer combinations of zip code and state than you'd expect because they're correlated, right? Almost all zip codes don't cross a state boundary. Whereas year and month are completely uncorrelated, so the number is multiplying the two cardinalities together. If we take all attributes combined, we'd expect them to have, probably, I don't know, 10 million or 20 million values, but the answer is only 912,000 because we're only sampling from 1 million records. Therefore, there can't possibly be more than 1 million combinations. So in the interest of time, I'm going to skip over this. There is an algorithm to design these summary tables based on the statistics. It's a pretty well-established algorithm. It works statically. You don't have to see what queries have been run. But it will produce something like this, which basically suggests the orange ones are the summary tables it's decided to create. And you can kind of see if you move from the top to the bottom by any particular path, you only hit one orange ellipse, which is obviously, if you think about it, once it's basically built. Actually, well, there's one down there. But once you, for example, built the year and month summary table, there's no particular reason to create the year summary table because year and month summary table is small and you can very, very easily roll up. So this is the optimization algorithm that it's doing, is choosing the right points to add these. Okay, so back to this idea of different people owning different parts of the data engineering pipeline. We introduced this idea of a derived table or a kind of a tactical ETL, which is the goal of which is to reduce friction, even though it might, let's say, circumvent the normal processes in the organization. Over time, we can restore order and basically take some of the ownership of some of these tasks can basically be moved upstream. So perhaps this thing that this analyst needed and they created using a persistent derived table on Monday, by Friday, or maybe by 2 months later, we've moved it into the official ETL process. So now we can get rid of that derived table. The user's happy because they've got the report. And the data engineer is happy because now it's moved into it's productionized, and it's being done as part of the nightly job, and it's more efficient. Lastly, we've moved one of the tables that was being populated by the system on demand from particular queries. Now we've moved that upstream, and maybe it's being populated as part of the LookML model. So we've anticipated that need rather than the system having to populate it on the fly. So what we've been talking about here is basically how to make systems adaptive. The goals are to improve response time and give people a rich model so they can ask the questions that they want to ask and get the results in a reasonable time. You also want the system to be adaptive so that you get maybe the first time you ask a new question it's slow, but the second time you ask it it's fast. Who does this? Well, really it's not possible for the system to do it, but it has to be kind of a combination of letting humans tune the system, let the systems adapt automatically, and then perhaps have some algorithms that will help with the tuning. And I've spoken of many adaptations. Materialized views are this very broad pattern of tricks, but caching data in memory is always an option, using secondary data structures like indexes, and other forms of reorganization like changing your file format. So that's all I have. Do we have time for any questions?
Do you see Calcite growing in its scope, or is the problem big enough that it covers right now to kind of, you'll be busy long term?
It's growing in its scope and its depth. So people are using it for federation, for example. We've had a lot of contributions recently from Alibaba, who are building a industry strength engine called Max Compute. They came out of the blue. They've been adding JSON support to implementing the JSON functions in Calcite. So the interesting thing about open source is you can't really direct where it goes. You get various people that join, and they have a particular thing they're interested in, and they contribute it, and it takes you into pretty interesting areas. All I can do, and the existing kind of members of the community can do, is try and steer it so that Calcite is not becoming something that it shouldn't be. But if we manage the code well, then it can be a lot of things. It can be many things to many different people.